In this video, we continue our quest to build an algebra of differentiation by figuring out what happens when we take the derivative of a product of two functions. So we have this function big P of x, standing for product, and that's defined as the product of f of x and g of x. And what we're trying to figure out here is, how do I write down the derivative of big P in terms of the derivatives of the individual functions f and g? And I think it's really important in this case to address how misleading our intuition can be. I think by far the most common first guess for how this works is that you would just differentiate f and differentiate g and multiply their derivatives together. Unfortunately, the derivative just doesn't behave in that nice simple way with respect to products. So I actually want to start here with a counterexample. Let's suppose that f of x is equal to x squared, and we'll say that g of x is equal to x squared as well. If we look at the derivatives of these two functions, they're both going to be 2x. And we found that by just applying the power rule to x squared. We brought the exponent down in front and subtracted 1 from the original exponent. So this means the product of these two derivatives is going to be 4x squared. But now we need to check to see if that really is the derivative of the product of these functions. So we can actually just calculate p of x before we take the derivative, and that's f times g, which is x squared times x squared, or x to the fourth. Applying the power rule to this, we find that p prime of x, the derivative of the product of these two functions, is actually 4x cubed. So the derivative of the product of the two functions is not giving us the same thing as the product of the two derivatives. Something deeper is going on here with how derivatives work over products. So to prove anything general about the derivative, we always have to go back to the limit definition of the derivative. And what we're looking for is the derivative of the product that we called capital P. So that's going to be the limit as h goes to 0 of p evaluated at x plus h minus p evaluated at x, all divided by h. And I'll post a link up at the top to where this was first derived. So now we just sub in the definition of big P, the product of f and g. So there's p evaluated at x plus h. We just replace the x's with x plus h's. There's p evaluated at x. And then we're going to divide this difference by h. Now, to just quickly discuss my motivation for the next move in a proof of this style, what I'm looking for in the numerator is like an f of x plus h minus f of x, or a g of x plus h minus g of x, because that's what the numerator looks like in a derivative of f or a derivative of g. So if I just focus on f first, I have an f of x plus h over here, but it's attached to a g of x plus h. And our f of x is attached to a g of x. So I can't factor and find f of x plus h minus f of x. What I need to do is actually throw a new term into the numerator that's going to make it so I can factor and find the difference I need to recognize the derivative of f. So here's where the magic happens. I want to have an f of x plus h minus f of x. So I'm just going to throw in a new term that looks like this, minus f of x times g of x plus h. Now I did that so that I could factor a g of x plus h out of both of those terms and then get the difference that ultimately leads to a derivative of f. And of course, you can't just go around subtracting f of x times g of x plus h from anything you want. You have to compensate for that by adding the same term. And finally, this minus f of x, g of x was a spectator in that whole process. And we divide everything by h. So now when I look at my first two terms, I see that I can factor a g of x plus h out of that, and I'll be left with the difference f of x plus h minus f of x. This is a good thing because we're going to relate that to the derivative of f. My second two terms also work out really nice. The common factor there is f of x, and if I factor that out, I get g of x plus h minus g of x, which ultimately leads to a derivative of g. So in the next step, I'm going to get a couple things done with the algebra here. First, I'm going to split this giant fraction into two fractions, one where we're focused on what's going on with f, and one where we're focused on what's going on with g. And at the same time, I'll do the factoring. So I'll pull the g of x plus h out of the first two terms and the f of x out of the second two terms. All right, so now I'm taking the limit as h goes to 0 of this whole thing, these two giant fractions, one with a g of x plus h factored out in the numerator, and then the leftover piece looks like the numerator of a difference quotient. In other words, this is starting to look like the derivative of f. In my second fraction, an f of x pulled out, and then a remaining piece that looks like the numerator of a difference quotient, but for the function g instead. So it's actually okay when you're doing a proof like this to just recognize that when I take the small h limit, this piece, f of x plus h minus f of x divided by h, is going to give us f prime of x by definition. And the g piece out here, well, that just becomes g of x when h goes to 0. But we can be a little bit more thorough with the algebra if we want to, where we actually explicitly show the derivative of f of x appearing as a limit. So what I can do is factor a g of x plus h out of this first one, and then the limit of a product of two things is the product of the limits. That was one of our original limit laws. So what I can do is rewrite this with a limit of g of x plus h separated out. So the first half of this thing turns out like that. I have the limit as h goes to 0 of g of x plus h multiplied by this limit as h goes to 0 of f of x plus h minus f of x over h. That second piece is exactly the definition of f prime of x, so the derivative of the function f. We get a similar term when we apply the limit to the second half of this expression. This one starts with the limit as h goes to 0 of f of x. And then we have the limit as h goes to 0 of g of x plus h minus g of x all divided by h, which is precisely the definition of g prime of x. So when I take the small h limit of g of x plus h, I can just replace the h with a 0 there. That doesn't cause any problems, and I just get g of x. The second limit in that expression, again, is exactly the definition of f prime of x. And then in my second half, I have an f of x, which is just a constant with respect to an h limit anyway. And then my second limit is exactly the definition of g prime of x. And so here's the answer. If I want to take the derivative of a product of two functions, I have to write down two separate terms, and in each one of them, I differentiate only one of the original functions. So I generally like to write all these derivative rules using Leibniz notation on the left-hand side. So I'm writing d dx of f of x times g of x. In other words, take the derivative of the product of these two functions. And then I'm going to mess with the order a little bit just because this is the way you normally see it stated in a textbook. So I'm going to take f prime of x, g of x, and then a second term where I have f of x, g prime of x. So now we know how to differentiate a product of two functions, and we can check out a simple example. But before I do that, I just want to mention briefly that there's a nice shorthand notation for all of this. And we can just use prime notation on both sides to write this down. And this is the way you might want to just memorize this because it's so much simpler without the proper function notation. So I'm writing on the left-hand side fg prime, in other words, the derivative of the product of the two functions. And then on the right-hand side, I go f prime g plus f g prime. Again, two terms, and in each one of them, only one of the original functions is differentiated. So here's our example. And the only functions we've learned to differentiate so far are actually polynomials, or you could call them linear combinations of power functions. So what we're going to do in this example is use the product rule to find the derivative of this product of two binomials, but then we'll also do this problem by just expanding this all into one giant polynomial and then applying the derivative. The two answers should agree with each other. So to use the product rule on this thing, we'll write down f prime of x is given by two terms where in each one of them you differentiate one of the original functions. Now we can actually use prime notation as kind of a placeholder. It's not always necessary to do this, but if you find yourself getting overwhelmed, you can just put a prime on anything that has to be differentiated later. So I'm just going to emphasize the product rule here by writing my first function prime times x squared plus 1 plus the first function left alone, so x cubed minus 3x, then multiplied by the derivative of the second function. So I can write that as x squared plus 1 prime. Now in the next step, I can do my derivatives. And I apply the power rule to each one of the terms in this first polynomial. X cubed differentiates to 3x squared. All I did was bring down that exponent out in front and then subtract 1 from the original exponent. Then I differentiate my second term, so I have negative 3 times the derivative of x, but the derivative of x is just 1. So I just get a minus 3 there. And the x squared plus 1 was a spectator on that whole operation. Now in my second term, I leave my x cubed minus 3x and I differentiate x squared plus 1. Differentiating the first term gives me a 2x, and then the derivative of 1 is 0, so that piece is gone. So we want to expand everything here and combine like terms, and ideally write it in descending order. It just gives us a uniform basis for comparison, and because we're trying to compare this with another method, we should put everything into the most standard form we can. So when I expand this first product, I end up with a 3x to the fourth plus 3x squared minus 3x squared. So our cross terms cancel here, and then I have a minus 3. Then I expand my second product, and that gives me a 2x to the fourth and a minus 6x squared. So we cancel the 3x squared and the negative 3x squared, and we're going to write everything in descending order here. So I'll start with my 5x to the fourth. So I have 5x to the fourth, and then minus 6x squared, and then minus 3. Okay, so there's the answer obtained by using the product rule. In other words, our new formula for computing the derivative of a product. The alternative here is to just expand this product before we ever take the derivative. So we're rewriting f of x, and we expand by using FOIL on these two binomials. And this would start out with an x to the fifth, that's x cubed times x squared, and then a plus x cubed, and then a minus 3x cubed, and then a minus 3x. So we can clean that up a little. I have x to the fifth minus 2x cubed minus 3x. Then we can compute f prime of x by just applying the derivative to all three of these terms. So I start out with my first one. The derivative of x to the fifth is 5x to the fourth, just using the power rule. In my second term, I'll just put an in-between step here. The derivative of x cubed is 3x squared, so I end up with a minus 2 times 3x squared. And then in my third term, the derivative of x is 1, leaving me with just a minus 3. So cleaning things up a little bit, I have 5x to the fourth minus 6x squared minus 3. And our two answers agree, and we're done with that example. In the next video, we derive a formula for the derivative of a quotient of two functions, in other words, an f of x divided by g of x. I've posted a link to that video at the upper left of the end screen, and I'll see you there.